so you know. This starts our chapter 15, 16. We're going to start, actually it's just 15. I don't think there's 16 at all. So just chapter 15. We're skipping 16, so the next one you'll outline is 17, just so you know. We're going to start talking about electric forces, so a little tiny bit of electricity, basic circuits sort of stuff, which we'll get into circuits in chapter 17. So today we're going to talk about charges. It's going to be very short. The homework is very short, so you get a nice little easy Friday. Don't get used to it. Okay, so we're going to define electric charge. We'll compare and contrast insulators and conductors, and talk about two different types of induction. So the first electric charges and magnetic charges were observed by the Greeks, and this was as early as 700 BC. They found that amber, when they rubbed it with like straw or feathers, it would become electrified and attract other small pieces like straw. And they also discovered magnetic forces by observing magnetite and found that it attracted iron. And if you look back at some of the really old Leyden jar stuff that they discovered in Baghdad, I think it was, and they were like stored type of battery things. There were some storing charges there. Kind of neat. Oh, they weren't Leyden jars.
Yeah.
They were jar-like items that were used as batteries.
The first
I don't know. You're talking about history stuff. I tell you the math behind it, but I'm really terrible at history. You could tell me a million times, I won't remember it. All right, the next person to work with electricity that really made a mark on history was Ben Franklin. Yeah. He did a lot of different things. I'm sure you've heard of him before. He's dead. Yeah.
Wow.
But he did a lot of work on electricity and some other things. I won't test you on this stuff. I won't test you on this stuff. I don't think the AP has too much stuff on this. It's just like you got to know names. Be a physical team. All right, so charge. This is the important stuff. The physics. Charge comes from atoms that are missing electrons or have extra electrons. So atoms with extra electrons are extra negative. They're very angry. And atoms that have lost their electrons are positive. So it's not that they have a positive charge, they have this positive, electron or whatever. No, they're just missing electrons. And if they have a negative charge, then they have extra ones. And charges can be singled out and added, so you can have monopoles, dipoles, quadruple poles, as many poles as you want. This is not the same as magnets. Magnets, for the most part, are dipole. You have a positive and a negative, or a north and a south pole. They were actually able to isolate a single monopole magnetic pole not too long ago, but it's really, theoretical, experimental type physics. It's not something that we learn down here. But charges can be any kind of pole you want. You just add another charge to it, and it becomes that. So, like a monopole would be like a positive charge. A dipole would be a positive charge and a negative charge. Quadruple pole, you have a positive, a negative, a positive, and a negative. It creates this beautiful flower-like. Yes?
Positive is when it's looking for an electron, and negative is when it's trying to get an electron, right?
Sure.
Okay.
That's very chemistry terms, but it is correct.
Okay, so we won't actually be using that.
Well, we'll look at it more of the terms as it's negative and it has an extra electron, and positive it's missing an electron, which is the same idea as chemistry, just phrased a little different. Never. All right, charge is quantized, meaning you can't have half of an electron. You either have an electron or you have 2 electrons, or you have no electrons, or you're missing an electron. They've got to be whole electrons. They're packets. That's what we mean by quantized. They come in packets. So all charges will end up being multiples of an electron's charge, which is 1.9 times 10 to the negative 9. I think it's 1.6. I think that's wrong. Let me double check that one. I don't trust that. Yeah, it's 1.6, not 1.9. A little dyslexic there. I clicked on 6. Coulombs, which is the unit for charge. Coulombs.
Sounds like Coulomb. Coulombi.
Well, you outlined it there. All right. So a positive charge, the charge of proton, so it's missing an electron, so it has a few more protons than it does an electron, is going to be a positive 1.6. And then if it has one extra electron, it's going to have a negative 1.6 times 10 to the negative 19 coulombs. All right. Charge is not going to be created or destroyed. You can only transfer electrons back and forth to change these charges around. So if you have gained a negative charge, you've taken that electron from something else, and that thing that you've taken it from is now going to be positive. Now, it might not be part of your system, so you can say your system has gained a charge or lost a charge, but it doesn't mean that it will be destroyed. It's just transferred in and out of the system. Same thing as conservation of energy. You're not really losing it or destroying it. It's just kind of transferred out of the system, so it's not really part of our system anymore. So conductors are things that let the electrons move easily across it. Most of your conductors are found in your metals, which are in the middle of the periodic table, because they're, pretty far away from filling that 8 electron shell. They don't really care if they gain or lose one, because they're kind of got like 4 or 5. It's not really a big deal. They're not just like missing one and they really want one. So your conductors, they kind of share their electrons, and they allow it to move across the surface pretty easily. What's interesting is conductors of electricity are also pretty good conductors of heat for the same reason. Because electrons, heat is just vibrating atoms, and electrons, when they're vibrating and they're shared electrons, they'll move to those other electrons really quickly. So that's why metals also tend to feel pretty cool to the touch, because they're not only conducting heat, they're not only conducting electricity, but they're also good heat conductors too, because of these free electrons. Now, insulators are the exact opposite. They're on the outer edge of the periodic table. They want to fill their electron shells. So they hold on to these charges pretty easily. Because they don't want to share, they don't want to give up their electrons, and they don't really want any extra electrons, they're not going to hold on to charge. Well, they're going to hold on to charge pretty well because they don't want to share them. Because now that they've filled their extra outer shell, they're going to be like, no, this is mine, you can't have it. So I'm going to try to stay negative. I'm going to try to stay positive because I don't, because I want it to be full. Yes?
If they hold on to it, what if they have like only one on top?
Then they want to get rid of it. Well, I mean, again, it depends on how many protons it has and how many electrons. It's going to be dependent upon whatever element you have. If it's, one that's normally missing one and it gains an electron to fill its outer shell, since it gained an electron, it's going to be negative, and it's going to tend to want to stay negative because it's filled its outer shell. Same thing is opposite. If it has an extra, so it's like the one like on the far left, and it has an extra electron, and with that extra electron it's neutral. But if it gets rid of it, now it only has 8 in the shell, so it wants to be positive. It's why salt works so well with itself, right? It has Na and Cl. Cl wants to be negative, and Na wants to be positive. And if they share those electrons, it can be negative and it can be positive. So they want to hold on to their electrons, so they'll hold on to their charge pretty well. They'll want to stay negative, or they'll want to stay positive, which is why it makes them insulators. Also, the same reason they want to, they're also good heat insulators as well, usually, is because they don't have, those electrons can't really escape, so they can't really vibrate other electrons to transport that energy. Okay, ready? We're ready? All right. For metal conductors, imagine a metal dome. In other words, a conductor. The charge is going to be distributed evenly on the outside of the surface of the conductor. And if the surface is smooth, they'll be nice and even. But if you have like a sharp point, like a teardrop or something, so let me draw you some pictures here. Here's a metal dome. If you have, let's say, a whole bunch of electrons, negative charges, it's going to be pretty much evenly on the outside edge of the dome. On the inside, you don't get charges. It's only on the outside. So even if it's on the inside, it's going to spread to the outside. If you have something like this that looks like a teardrop, you're actually going to end up, down here, they'll be pretty even. It doesn't matter what charge you have. But up here, you're going to have a fairly dense, compact thing of charges because it comes to a point. So they tend to accumulate towards that sharp edge. The electric field produced by these electrons, which you can feel if you put your hand near one of those Van de Graaff generators, which I have one. You'll have to remind me at the beginning of the next class, and I'll bring it out, but you have to remind me because I'll forget. If you put your hand near something electrolyzed like that, charged, you can actually feel the hair on your hand like move around. That's the electric field. It's interacting with the hairs on your hand because of the charges in it. And it's probably either attracting them or pushing them away. Like when you put your hand on them, your hair goes everywhere. Is that charge is affecting, it's spreading. You're being affected by that electric field. That's it. Well, this electric field is always perpendicular to the surface. So the electric field is going out from the surface like this. Same here. Perpendicular. And we'll learn how to calculate this electric field a little bit later. Not in this lesson. Okay. So a Van de Graaff generator, which I have one of these, and if we have enough time at the end, I'll probably pull it out so you can look at it. The belt might be broken on it, so we'll see. It's an electrostatic generator. It was designed by Robert Van de Graaff in 1929. We have a belt in here. It's a rubber belt, I think, and a little tiny brush. And this belt goes up here and goes by the brush, and the brush scrapes off the electrons. It takes these electrons and it's grounded, so it's translated, it's transferred out of the system. That leaves the belt positive, and the belt then comes up here and it transfers these positive charges to the dome. And because it's a charge, it's going to go to the outside of the dome, and it's going to spread itself evenly. So you get a bunch of positive charges on the outside of this dome. And eventually, if this charge builds up enough, you can get pretty close to it and go bzzz, and it'll transfer. What it's doing is it's stealing your electrons so it can become more neutral. So that's that little zap that you feel. It's a transfer of electrons, and moving electrons is electricity. Yes?
Is that it trying to steal electrons from you, or you trying to steal electrons?
Depends on which one's more positive, if it's positive or if it's negative. I don't know which way it would be.
Yeah, both very different.
Yeah, it's both a transfer of electrons, and either way it's going to shock that. It depends on the material. I'm thinking it's probably a lot like this. It's probably positive, if I had to guess, but I don't know. You have to do some testing and figure out what it would be. All right, charging by conduction. Okay, the picture is really the easiest way to do this. So imagine you have a normal metal sphere. It's not connected to anything. It's not connected to the ground. It's just kind of floating up here. It's this metal sphere. It's neutral, but I have a charged rubber rod, and the charged rubber rod is negative. It has lots and lots of electrons, extra electrons to make it negative. So if I put that rubber rod near the sphere, what's going to happen is the negative electrons are going to be repelled to the other side, and those electrons are going to be repelled to the other side. And on this side, we're going to have the positive parts exposed of those atoms, because all the electrons went away. It's not like the positive charges. They're not charges. They're, missing electrons. So the electrons basically move away. And since positive attracts negative, this sphere steals the protons so that it'll be neutral for the most part, as it can be. So now it's going to have extra electrons when we move the rubber rod away. Because this was neutral first, and then it stole electrons from the rubber rod so that it could be as neutral as it possibly could get. And then we take the rubber rod away, and we're left with excess negative charges. So now it is charged. So it wasn't charged up here, but now it is charged down here because we have the rubber rod which was charged and moved and transferred these electrons to make it charged. So that's one way to charge, and this would be charged by conduction, when you're actually touching the rod to it. Yes?
So the negative sign, that is not negative, it's neutral?
No, it's negative. It's an electron. What I'm saying is when it started out, it's neutral. It has the same number of positive charges as it does negative charges. And then when we put the rubber rod on there, this positive charge sucked in these electrons so that it could be neutral. And then we took the rubber rod away, and it has excess negative charge now. All right, now we have charging by induction, which is very, very similar, except for you don't actually touch. Right? The conduction you're touching, induction you're not. So we have our metal sphere. It's neutral. It has the same number of protons as it does, positive charges as it does negative charges. Not necessarily protons and neutrons. Then we have this charged rubber rod that's negative, and we put it next to the sphere without touching it, and it's going to push those negative charges away from it. So all the electrons are on one side. Now we can hook up our sphere to a wire which is called a ground wire. That's what this picture is right here. And that ground wire is hooked to the Earth. And the Earth, it has so many protons and electrons that gaining a few is really not going to change anything. So it tends to be either supplying electrons or taking electrons depending on what you need to do. It's just imagine it's a giant storage container of electrons. So we're pushing the electrons out of the sphere by putting this rod here, because they want to get as far away from the negative charges as they can because they're repelled. So the Earth sucks them up if we hook it up to the Earth. And then we'll take the ground wire off, and we have our negative rod here. So it's not going to steal all the electrons, but it's going to steal as much as it can. And then we'll be left with a fairly positively charged sphere. So we didn't touch. That's the difference. We didn't touch, and the Earth took our extra.
Wait.
Oh, okay, it's negative to begin with.
The bar is negative to begin with.
Okay, so...
This is neutral.
Okay, if it's neutral, then you take away electron, couldn't it be
Positive. Yeah, positive charge down here.
Okay.
Mm-hmm.
I thought you said it was neutral.
No. All right, and that's pretty much all we have. I have some clicker questions for you. Here you go. And while you guys are answering the clicker questions, I'll try to bring out that in the graph generator. So here's our first one.